And we're live from Pierce 116 on Monday night, March 19th. And we're here to discuss circuits. What else could be more interesting? We're up here for the Exam 2 review, and our audience is primed and ready to go and ask questions. So my goal for tonight is to make this worth your time, both the home audience and the studio audience. So what we're going to do is to go through one exam. I thought a real good exam to do would be last year's Quiz 2. So Spring 2017, Quiz 2, and we're doing version 1. Okay. Later on this evening, the last problem, I'm going to pull a problem from version 2. But we're going to do all 3 problems from version 1. Now, some of you know my secret. Dr. Kevin Ryan is version 1. Dr. Kevin M. Ryan is version 2. So that's how we can always tell just by looking if it's version 1 or version 2. This is version 1. So I say, great, let me get started. And I slide down. And I see that there are 3 problems. And remember, this exam, Exam 2, is going to cover Chapters 3 and Chapter 4. But really, it's Chapter 4. Because Chapter 3, all we have to know is the 2 chants. I equals CdV dt, and V equals LdI dt. Now, before I start, I want to take a moment to thank our dedicated colleague and volunteer, Jonathan, who's sitting in the back and working the camera. And there's also out there, Jonathan's giving our thumbs up, and there's also behind the scenes, there's Jesse and Sean and Matthew, and I hope I'm not forgetting anyone else. So I want to thank SITTV for making this recording possible. Jonathan and SITTV, thank you. All right. All right. So I look here and say, great, what do we got? First order, second order, and we come back for another first order circuit. Boy, this looks great. So I say, let's just dive right into it. Now, studio audience, don't hesitate to ask questions. So I look at this crazy circuit, and I say, oh, Tiger, this looks hard, but it isn't. You're all going to be able to do it. Okay, so I'll give you a moment to just copy it. Again, all these exams I checked this afternoon. They're all posted on the course website. So I'm looking here, I see switches, so I'm going to have to read the problem carefully to find out which switch is open or closed. So Michael is back there taking notes. All right, now I'm just going to read the problem to make sure I know what it's asking for. We have 2 voltage sources, and each is a constant. That's nice. That's going to make the problem easier. Now, it says here the circuit has been operating for a long time. Ryan, that's my way of saying steady state, 5 tau. Exactly. When you see that it's been operating for a long time, it's in steady state. So it's been operating for a long time with switch 1 open and switch 2 closed. Now, hopefully you're comfortable with the notation. Switch 1 closes at t equals 0, and switch 2 opens at t equals 0. Okay. Now, question part A. Write the first order differential equation in standard form for V1 of t for t greater than 0. Now, what I do is I like to make sure I don't make a mistake. I draw the circuit for t greater than 0, just to make sure I know what's going on. So for t greater than 0, this switch is closed. Okay, fine. But this switch is open. And what am I asked? To solve for V1 of t. So I am asked to write an equation for V1 of t. V1 of t is over here. And switch 2 opens at t equals 0. So my colleagues, everything to my right has no impact because switch 2 is open. It's gone. So Emily, I just need to focus over here. So to make sure I understand this problem, I'm going to walk over here to the side of this board and I'm going to draw the circuit for t greater than 0. So I'm now going to walk over here and I'm going to write the circuit for t greater than 0. So what I notice is I have R3 and then I have a capacitor. Okay, that's C. And then I have R2. And we come into R1. And then we go into the voltage source, which is VA. And this is ground. And there we have it. Now I have to add, where is V1 of t? Tara, you know this. V1 of t is this node, but it's all of this, right? Because it's just a single wire. I overwrote the subscript here. Let me correct that. This is V1 of t. All right. Now, the next thing I notice is that R3, there's no current going through R3. Why? Jonathan? Right, it goes right into the capacitor. There's no current going here because if current were to flow this way, it's a dead end. Can't come around, can't come back. So there's no current through R3. So I put myself in the node. Oh, Parker, why am I putting myself in the node? Because I'm looking for voltage. So I'm going to put myself in the node. So I put myself in the node and I say, unless I'm told otherwise, current goes out, current goes out, current goes out. So now I'm in that node. There are 3 branches where the currents flow. And I'm going to write the equation. What's the current through the capacitor? Easy. I equals CdV dt. So the current through the capacitor is C dV1 of t dt. Now please stop me, my colleagues, if there's the slightest doubt. Next, what's the current through R2? V1 of t over R2. Plus, what's the current through R1? I think it's V1 of t minus VA over R1. So I get V1 of t minus VA over R1. And all of this equals 0. Now let me pause. If you got this wrong on the exam, you're going to get almost everything else wrong. So it's really important to make sure that you're comfortable with writing this equation. I welcome any questions. Now, to my colleagues in the home audience, notice the first thing I did. I read the problem and I said they're looking for V1. Now, which side of the circuit is V1? The right. Then I said, okay, I'm going to draw it. I'm going to draw it with the switches in the proper position for t greater than 0. So really, to me, the most important part of this problem is going from this circuit drawing to the circuit drawing that I have here. Once I did that, I said, okay, I got this. I can then write the equation. Now, what's the next step? I hear it. Someone just said it out there in the home audience. Someone was yelling standard form, okay? So I said, okay, I now have to get this in standard form. Tiger, you know and I know the standard form is a 1 in front of the non-derivative term. So let me just take a few moments here. I want to do it step by step so there's no confusion. This is V1 of t times 1 over R2, okay? And then this is V1 of t times 1 over R1. I'm just, making it so it all, then VA times 1 over R1. I really haven't done much here, just broken it down to individual terms. Now, what do? What I have, I'm going to run over here to the other side of the board. And what we have here on this other side of the board is C dV1 of t dt plus V1 of t outside of 1 over R1 plus 1 over R2. 1 over R1 plus 1 over R2. And this then equals VA over R1. My colleagues, am I good so far? All right. Next term, I just want to combine this here. This I can write as R1, R2. And this then is R1 plus R2. Now, Tiger, as you yourself told me, I need to get that coefficient in front of V1, the non-derivative, to be 1. So what do? I multiply everything by the reciprocal of this term. So multiplying by the reciprocal, what I get is R1, R2, I know I'm blocking up, whoops. Yeah, yes, I'm doing it right. R1 plus R2 times C times dV1 dt plus V1 of t. Now, don't forget the right-hand side. This then becomes R2 over R1 plus R2 times VA. This should be the answer to part A, which was write the first order differential equation in standard form for V1 of t for t greater than 0. I think we've done it. Now, while you're writing that down, let me check my solutions. I would be very embarrassed if I'm wrong. R1, R2, R1 plus R2, times C, dV1, boom. Looks good. Let me pause. How are we doing? I think I have a question. I think someone has a question. I want to help. Tara, I'm just guessing. You might have a question. You might not. No, Tara, there's no unintelligent questions. I learned that in professor school. So help me out, Tara.
For some reason, I don't know if it's because like what we did today. I thought it was that first term that you wanted to isolate. But
Tara, that's excellent. My colleagues, if I'm over here on the board, Tara is saying, wait a minute, we had a fantastic lecture today. And I thought in today's lecture, which is Monday the 19th of March, that we wanted a 1 in front of the highest order derivative term or something like that. That is true for second order systems. For first order systems, if I could run over here, for first order systems, we want this coefficient here to be 1. which is the coefficient on, and I'm going to run over here. So we want the coefficient to be 1 in front of the non-derivative term. Tara, for second order systems, we want a 1 in front of the second derivative. Now, we're going to see the second derivative in the next problem. Tara, did I do okay? All right, so for first order systems, Ryan, we want a 1 in front of the non-derivative term. Okay, it's looking good. All right, now, part B. What is the time constant for this system? Dun, dun, dun. Fantastic, Tiger. You got it. If you have it in standard form, Tara, if you have it in standard form, whatever is in front of the derivative term is tau. Simple as that. An easy 2 points. So what is tau? Notice it's RC. But RC is product over the sum. That's an REQ. So it's RC, except it's some combination of the resistors. Are we good? We're good. We're good. We're good. Now, next question. What is the homogeneous solution? You got it. Help me out. That's the particular solution. You know what it is? We're going to come back to you in the next question, and you're going to get that. Because the next part says, what's the particular solution? You got it. What's the homogeneous? Jerry. Right, it's St. Kevin. All right? But S, we know now. We know it's KE, and we solved for S. Michael, we had so much fun doing it. We spoke about it. It was so much fun. We know that S is, well, it's KE to the minus T over tau. Okay? So what happens is you can write it down. You don't have to derive it. I know this is disappointing you, but you don't even have to derive it. We derived it at least once in class. We may have done it twice. So V1 homogeneous is KE to the minus T over tau for T greater than 0. What's tau? Part B. Now, solution to a first order differential equation consists of the homogeneous and the particular. Now, you're going to think I'm a little devious here. I asked in part D, determine the value of V1 as T approaches infinity. Is that the particular solution? But first, wait a minute, I think we have a question. I sense a question.
Yeah, I actually do have a question.
Help me out.
So, when you KE to the ST, which makes sense, where did you get the negative T, like negative T over tau? That's where I was confused.
Right, excellent question. So the question is, you got the KE to the ST. So you know that the homogeneous solution is KE to the ST. Absolutely. Now, what you do is you take KE to the ST and you walk over to this side of the board and you substitute it into this equation, setting it equal to 0. And you will then solve for S. Okay? And what you'll get, walking over here, is we have KE to the minus T over tau. So what we find is S is minus 1 over tau. Now, you don't have to prove that. It's very simple to prove it, and we did it in class at least once. So how do I get it? Take KE to the ST and substitute it into the other equation, but set it equal to 0 because it's the homogeneous solution. Okay. And you solve for S, and you get that S is minus 1 over tau.
Is it always going to be negative T over tau?
the question is the homogeneous solution always going to be Ke to the minus T over tau? The answer is yes for this course, because we look at a subset of differential equations. They're called linear with constant coefficients. In that special case, it is always Ke to the minus T over tau. So for first order, it's Ke to the minus T over tau. We'll see a little more complicated answer with second order coming up next. All right? All right, so far so good? All right, now, so the value of V1 as t approaches infinity. My colleagues, that is the particular solution. I just asked it in a different way. So what happens as t approaches infinity? We approach the particular solution. And as we have already been told, and we are right by Daniela, we know that the particular solution is the right-hand side. So notice what happens as t approaches infinity. We go to the right-hand side, which is R2 over R1 plus R2 times VA. Okay, we're doing good. We got 2 more parts to go. Now, let me just show you something, just for fun. I'm going to walk over to this side of the board here. And my colleagues, forget about all the math, just for a moment. What happens? After 5 tau, everything's in steady state. And Tiger, when we're in steady state with a DC input, what does a capacitor look like? Fantastic. This capacitor becomes an open circuit. So there's no current flowing. So after 5 tau, this is what the circuit looks like. So where is there current flowing? Here. Now look at this. This is great. You're going to say, wow, this is wonderful. What's the voltage across the capacitor? The capacitor is in parallel with R2. What's the voltage across R2? Parker, voltage division. The voltage here, this voltage right here, is R2 over R1 plus R2 times VA. Michael, that's what we derived with math. This stuff is great. Okay. So what we get is we get the same answer for the particular solution by just looking at it and saying the capacitor is an open because it's in steady state with a DC input. And what we get then is just the voltage division, which is R2 over R1 plus R2 times VA. I think this is a lot of fun. Now, we're up to the next part. We got 2 more parts of the problem to go. Okay. How are we doing so far? Yeah, so that's right. I'm glad you stopped there, Michael. That was good, right? If you're in a lot of trouble if you get the first part wrong. So it's good to take your time on the first part. Okay. Now, it says determine the complete solution. So I say, okay, wait a minute. I got to determine the complete solution. Now, in the meantime, I want to put this up again, okay? So I'm going to walk over here to this side of the board, and I'm going to say, all right, what do I know so far? I know that for a first order differential equation, the total solution is the homogeneous plus the particular. So what I have is V1 of t is the homogeneous Ke to the minus t over tau plus the particular, which is R2 over R1 plus R2 times VA. I know everything but what? VA is given. That's a constant. I don't know K. Now, how do I get K? Initial condition. Now, to the home audience and the studio audience, this is most important. So please, give me your extra special attention. I want you to get this right. V1 of t is the voltage across a capacitor. Right? Now, I say, wait a minute. What I want to solve this problem is this. V1, Tiger, V1 at t equals 0 plus. I want to find that out. Because, Ryan, that becomes the initial condition. I want to get V1 at t equals 0 plus. But Ryan, that's the voltage across a capacitor. What do I know about the voltage across a capacitor? CdV dt, that's the current. And all right, Ryan, let's go with that. I equals C dV dt. Ryan, that's a current through a capacitor. Now, Ryan, help me out. If the voltage were to change instantly across the capacitor, what is the slope of this line? Infinity. What would happen to the current? Infinite. We're talking like Nobel Prize. That's not going to happen. Okay? So that is why the voltage at t equals 0 plus equals the voltage at t equals 0 minus. Now, you don't have to know this. You don't have to, you don't have to know why. I think it's fun to know why. All I want you to know is voltage at t equals 0 plus across a capacitor is the same as the voltage at t equals 0 minus across the capacitor. They're the same voltage. And the argument is if they weren't the same, we'd have a spike of infinite current. Okay. Now, Ryan, why is this so important, Parker? I need to know the voltage across the capacitor at t equals 0 plus. As I will show you, it is a lot easier to determine the voltage across the capacitor at t equals 0 minus. It's a lot easier. So I look at this and say, okay, what is the voltage across the capacitor? Michael, I'm thinking of your comment. Don't mess up here. You got to take your time and make sure we get it right. What is the voltage across the capacitor at t equals 0 minus? So I say to myself, wait a minute. What does the circuit look like at t equals 0 minus? So Emily, at t equals 0 minus, this switch is still open. So this doesn't have any impact at all. At t equals 0 minus, this switch is still closed. Now, what do I know? If something has been closed for 5 tau, steady state, and with a DC input, the capacitor becomes open, the inductor short. Very good. So redraw this circuit. Redraw the circuit. I'm drawing it on the board. Here's the inductor as a wire. I then go through R3. I then go through the capacitor. Capacitor is open. I then go through R2. I then have R1 and then VA. This is VA. This is R1. And this is the voltage that I want. This is the voltage across the capacitor at t equal 0 minus. So I say, okay. I now have to get that voltage. I think R3 and R2 are in parallel. How do I see that? Same node here and the same node here. R2 and R3 are in parallel. So I can define, and stop me please if I'm not making sense, I can define an REQ. The REQ is going to be product over the sum. So I no longer see two resistors, R2 and R3. I see one resistor. So now what I have, God bless, is this is the capacitor. This is REQ. And this is R1. And this is VA. My colleagues, I'm going to walk over to the other side of the board here to erase it to write the answer. But I need someone to help me out. What is an expression for the voltage across the capacitor at t equals 0 minus? What do you think? Excellent, Tiger. Voltage division principle. And we get that V sub C at t equal 0 minus equals REQ over REQ plus R1 times VA. Now this equals K e to the minus t over tau, but what's t? 0. All right, plus, I need someone's help. Was that R2 over R1 plus R2? Did I get that right? Times VA. So now, my colleagues, solve for K and then substitute K back into the total solution. Let's now look at my solution so we don't have to write it all on the board. Here is K. Going back to the screen here, K is this minus this, which I think we can see from here. REQ over REQ plus R1 times VA minus R2 over R1 plus R2 times VA. Excuse me, sorry about that. And what do we now do? Plug it in. K e to the minus t over tau plus the right-hand side. Plug in for K, and we're done. We still got one more part to go, but that gets us through almost the whole problem. I'm seeing quizzical faces. I just need help with your questions if you have any. Michael, help me out. So 0 came from the fact that we're evaluating this at t equals 0 plus or t equals 0 minus. Right? So what we have is, and V sub c at t equals 0 minus equals V sub c at t equal 0 plus. No, that doesn't equal V1 of t. That equals this, what we just derived, REQ over REQ plus R1 times VA. So that becomes the voltage at t equals 0 minus, which is the same as the voltage at t equals 0 plus, because it's the voltage across the capacitor. And now I set that equal to K e to the minus t over tau, but t is 0, plus the particular solution. And now I can solve for K. So K is this quantity minus this, which is exactly what we got. How do we do, Michael? Good, thanks. Jerry, help me out.
So you're allowed to have like REQ in the final answer?
Yeah, as long as you tell me what REQ is. Okay, I think that's fair. You just can't write REQ. You got to put right underneath it what it is. Good. Yes? Great. Can I go over why R3 and R2 are in parallel? So I know I wrote it on the board, which I'm going to go back to. But let me also show you in the notes where we have it here. So maybe I can look at this figure now. Okay, so if I go back to the screen, this is the capacitor, and it's an open circuit. And I have the inductor as a short circuit. So I have R3. Now, R3 goes from this node to the bottom node. R2 goes from that same node on top to the same node on the bottom. So they're in parallel. I'm wondering if I were to redraw it. With your permission, I'm going to walk over to this side of the board. How about if I were to draw it this way? Now I can see it, right? Now I can see that R3 and R2 are in parallel. Did I do okay? Good. All right. Believe it or not, there's one more part to this wonderful problem. So we solve for all time. We solve for everything. We solve for the initial condition, the complete solution. Part F. Write the first order differential equation for the voltage across the inductor for t greater than 0 in standard form. Parker. I got to go back to the original circuit. Write the differential equation in standard form for the voltage across the inductor for t greater than 0. So Tara, I say, all right, last part of the problem. I'm not going to blow it now. So here. I look here and I say, they now want the voltage across the inductor for t greater than 0. So Tara, what I do is I'm going to walk over to this side of the board and I'm going to draw the circuit for t greater than 0, just so I know what's going on. Now, what am I asked to solve for? V sub L of t. So, Ryan, I'm going to solve it for t greater than 0. For t greater than 0, Ryan, do you and I agree switch 1 is closed and switch 2 is open? So, if switch 2 is open, everything here is gone. So, what I have is for t greater than 0, I have this circuit. And I now want to get V sub L of t. Now, let's see if we can figure this out. Since I want nodal, since I want voltage, what technique are we going to use? Nodal. Okay. So I put myself in this node up here because I want to get V sub L of t. And that's the node. So I think what we get is V sub L of t minus Vs over r. Now, by the way, for this one, all you have to do is to write the equation. You don't got to solve it. I thought you'd be running out of time at this point. So we're just going to write the equation. So we got V sub L of t minus Vs over R. That is this current here, leaving the node going through the resistor. Now, be careful. What is the current going through the inductor? Sorry? No, that's the voltage. So if we want to get the current through the inductor, what do I know? Fantastic. Who was that? Was that you, Ryan? V equals L di dt. But Ryan, this is a great beginning, but Ryan, I want I equals something. What do I got to do here? I know what we got to do. I know. I want I equals, not V equals. So, I've seen this done in class. Does that look okay? All right. I just wrote it this way. Ryan, how am I doing? Ryan, what do I do next? Take the integral on both sides. Now, Ryan, what does the right-hand side then become? I at t minus I at t equal 0 plus. So what do I have? I get that I of t equals 1 over L, the integral from 0 plus to t of V sub L. Let me make that a little clearer, my handwriting. V sub L of t dt. And then I bring this over, so this becomes I at t equal 0 plus. Let me stop. Help me out. Are you comfortable with this? Are you able to follow this? What can I do to help you? I see a thoughtful question. What do I need here? I need current. I need the current through the inductor. So I'm writing on the board here that I need the current through the inductor. And all of this equals 0. But I don't know what the current through the inductor is. But what do I do know? V equals L di dt. So solve it so I equals something. How do I do that? Divide by 1 over L. Or divide by L, excuse me. Divide by L, multiply by 1 over L. Divide by L. And then integrate, and I get I of t equals this. All right. With that in mind, let me now walk to the other side of the room here. Okay. I'm now on the other side of the board, and I'm now going to rewrite this as V sub L of t minus Vs over R plus the current. Oh, I just solved for the current. That's 1 over L times the integral from 0 plus to t of V sub L of t dt, then plus that initial condition term, which is plus I at t equal 0 plus. And all of this equals 0. We're almost there. We're almost there. I then look at this and say, what do I get here? I get 1 over R times V sub L of t plus 1 over R times Vs plus 1 over L 0 plus the t. I have this integral. Michael, how do I get rid of this integral? I take the derivative. So my colleagues, I take the derivative. Okay? I take the derivative. Taking derivative of the first term, I get 1 over r times the derivative of v sub L of t dt plus, Vs is a constant. What's the derivative of 1 over r times Vs? 0. Plus, I take the derivative of this. What I get is just 1 over L times the integrand, which is v sub L of t. Tara, how am I doing? I then get this term here, which is a constant. That's plus 0 equals 0. So now what I get is L over R times the derivative of the voltage across the capacitor as a function of time plus V sub L of t equals 0. Did I get it right? Yeah. Okay. And again, all these solutions are posted, my colleagues. Now, Parker, one of the joys in teaching a large class is that some people might have said, gee, I can do this with mesh. And I'll leave this to you, but you can. So if you wanted to do it with mesh, it turns out you're going to get the same answer. Okay? That's problem 1 done. Now, you might be saying, this took 50 minutes to go through. We only have 50 minutes for the exam. What's happening here? Okay? So we're now up to problem 2. Are we okay on problem 1? All right, problem 2 is a second order system. And it's very similar to what we have done today, Monday, in our lecture. So while you're writing it down, let me erase the board. And I think you'll see a lot of... I'll start erasing on the other side. What was I thinking? Okay. All right, I'll start erasing over here. Okay. Now, for those of you who were in lecture today, and I know just about, I think everyone here was, I said there's only 2 ways I know how to ask you about this problem. To either solve for the current or the voltage. All right? So, it says here, write the second order differential equation in standard form for the capacitor voltage. For the capacitor voltage. Jonathan, is my audio still good? We're still good, thanks. All right, so let's write this for the capacitor voltage. Now, you won't find this X on the exam. You will find it on the solutions. In this course, when I ask you to solve a second order system, what do? Take a walk. So I'm going to start at the bottom left. You could start anywhere. I get minus Vs plus the voltage across the resistor, R times I of t, plus the voltage across the inductor, L di dt, plus the voltage across the capacitor. Do not write that as I equals C dV dt. Some people write C dV dt. That's the current. I equals C dV dt. I just want the voltage across the capacitor. I'm good. All of this equals 0. I'm off to a good start. However, I'm asked to find the equation for V sub C of t. I notice I have I of t, which I don't want. So you might remember from today's lecture, what do? Or I don't know if I did this. I think I did. What do I do to get rid of I of t? Excellent, Emily. We do a substitution of variables. What do I know? I of t equals c dv dt. Why is that true? We have a series circuit, and the current goes through the capacitor, so it must follow I equals c dv dt. And now I say, great, this is a series circuit with series circuit with the current flowing through it. Each element gets the same current. We must have I equals c dv dt. So what I now do is I substitute. So I get minus Vs plus R times I. What's I? C dv dt. Plus L di dt. L di dt. I got to take the derivative of that, which is C times the second derivative plus V sub C of t equals 0. Now, Tara, I am now reminded of your comment from before. I now want to get this into standard form. I want a 1 in front of the of the second derivative. A 1 in front of the second derivative. So rewriting this, I get the second derivative of V sub C of t dividing by LC plus RC divided by LC is R over L times the derivative of V sub C of t dt. Now I'm dividing everything by LC, so I get 1 over LC times V sub C of t equals Vs over LC. I know I'm going through this quickly. We've seen this today, but all of the algebra is carried out in the notes also. Let me pause and give you a moment or two to catch up and ask me any questions you might have. Michael. The point of taking the second derivative, you mean taking the first derivative? No, you're right. The point was, Michael, we have I, and V. I'm asked to only have V. So I do a substitution of variable. I is C dv dt. So when I plug it in here, I don't want I want di dt. So I got to take the derivative of this again. And that gives me the second derivative of the voltage. Let me back up, make sure I say all the right points, Michael. I have I and V in the same equation. We only want V. But I know that I is related to V in this equation here. So, Michael, wherever I see I, put in this equation. So R times I becomes R times C dv dt plus L di dt. I know I is C dv dt, so derivative of I is C, the second derivative of the voltage with respect to time. Michael, did I get it? Good. I've lost track now. Let me get my senses back. I need to just erase this over here. So it says here, Tara, have we done part A? It says write it in standard form. I think we've done it. Okay? So let me slide down. Before I do that, that should be the answer. Second derivative with respect to time plus R over L times the first derivative plus 1 over LC times V equals Vs over LC. Good. Now, let's try part B. Part B says, you are given the value of the resistance is 30 ohms, and the value of the inductor is 10 millihenries. Determines the value of the capacitor for the second order to be critically damped. Before we go any further, Tara, help me out.
Well, two things. First, did you mean to square the DT in the bottom of the second row when you have the second order? Did you square it?
Okay, let me walk over here. Tara, you're absolutely right. Forgive me. I think you're referring to this here.
Yeah.
Tara, my bad. I should have squared it. Perfect.
Okay. And then the LDIT over DT that we got in the beginning, is that like a chant? Like I'm just forgetting how you know that's the term.
Right. So, excellent question. Tara, if you take a walk, it's minus Vs, the voltage. Then the voltage across the resistor is R times I. The voltage across an inductor is V equals L d I dt. So that becomes the voltage across the inductor plus then the voltage across the capacitor. Tara, did I do okay?
Yeah.
Anything else? Thank you for your two helpful comments. All right. Now, I need to determine the value of the capacitor for this system to be critically damped. Does anyone remember? Critically damped means zeta equals 1. Now, what was zeta? Zeta was alpha over omega 0. Now, there's a formula sheet. You don't have to memorize what I'm about to tell you. But it turns out that this term right here in front of the first derivative is 2 alpha. So 2 alpha is R over L. So alpha equals R over 2 times L. And we know what R and L is. R is 30 ohms. And then it's 2 times, now be careful, that's 10 millihenries, which is 10 times 10 to the minus 3. That's what alpha is. We have the numerical value worked out in my notes. Now, what's omega 0? Omega 0 is 1 over the square root of LC. So, let's take a look at this. I think we got this. Okay? Alpha is R over 2L. Omega 0 is 1 over the square root of LC. What's zeta? Alpha over omega 0. I want zeta, Michael, to be 1 because it's critically damped. So plug in all of these variables. Zeta is alpha over omega 0. My colleagues, I know this looks confusing. It's not. It's just basic algebra. I know you can do this. And what you get is after you look at all of this, you get that C has to be 2 times the square root of L over R. I know L and I know R. I plug it in. I got it. Jonathan, how we doing back there? You doing good? Ryan, how are you doing up here? So now we have an expression for the value of C, which is what we were told or asked to find. And if I just continue on, C is now 4L over R squared. I give you R, I give you L. So it's 44.4 microfarads. Are we good? Tiger, we're almost done, are we? Yes.
Wait, could you, what was the answer?
Sorry, here? You're very welcome. All right. Last part. You are now given that the second order circuit is critically damped. In addition, you are given the following two initial conditions. Now, for my colleagues in the room here, this is what we're going to discuss in Thursday's lecture. So don't be a little confused or discouraged if you're confused at this point. We haven't yet officially covered this in the lecture. This is where we left off today. So it says here, you're given two initial conditions. From the given information, determine the numerical value of K1 and determine an expression for K2. All right. Here, let's go back to part A. This was the equation we wrote for the second order system. If I tell you it's critically damped, what's the homogeneous solution? If I tell you it's critically damped, what's the homogeneous solution? Jonathan? No, not 0. Nope. Sorry. Very good. Emily, excellent. Excellent. Emily, V sub C of t equals K1 e to the st plus K2 t e to the st. Now, you might say, wait a minute, how do we know that? If you go to the formula sheet that I have at the end of this exam, here, for zeta equal 1, it's K1 e to the S1t plus K2 t e to the S1t. So now that becomes the homogeneous solution. Now, this we did cover today. Does anyone remember what the particular solution is here? How do I get the particular solution? Ah, you know. You know, it's just getting late. It's just getting late. You know. V sub c particular of t is a constant. Why? Because the input's a constant. So I've used K1 and I've used K2. What's the next constant? K3. Parker, help me out. Parker, I now take K3 because it's a solution. And I come over here and I plug it in for V sub c of t. So Parker, second derivative of K3. K3 is a constant. Second derivative is 0. First derivative, 0. What I get is 1 over LC times K3 equals Vs over LC. Value of K3 is Vs. So it turns out that this particular solution is Vs. That means this is the solution to our equation. How am I doing? All right. So now, so that's what I have here, my colleagues. The total solution is K1 e to the st plus K2 t e to the st plus V sub s. V sub s is 10. Let me stop. I know I'm hitting you with a lot. How are we doing? Now, I have to solve for K1 and K2. What do I need? Two initial conditions. Two initial conditions. Now, the first initial condition I need is V sub c at t equals 0 plus. That's the first initial condition I need. See, I have V sub c at t equals all of this. Emily, what I want now is V sub c at t equals 0 plus. So I look and say, by any chance, was I given this? Yes. Yes. It's 2. So what do? I plug in 2. Michael, I'm thinking of you back here. This equals K1 e to the st. What's t? 0. Plus, K2t e to the st. What's t? 0. So this goes to be plus 0 plus 10. K1 is 2 minus 10, which is minus 8 volts. Tiger, how am I doing? All right. I'm looking around the room. All right. Next. The next condition I want is the derivative of V sub c of t with respect to t evaluated at t equal 0 plus. Now let me stop. Some of you may be hearing this for the first time. Some of you may have had this before in Diffie Q. If you have a second order solution for V sub c of t, Tara, the two initial conditions I would like is V sub c at t equals 0 plus. And the next one would make life very easy for me, is the derivative of V sub c of t evaluated at t equals 0 plus. That would be wonderful. I would absolutely love that. So I come over here and say, okay, what am I given? I at t equals 0 plus. That's not what I want, Ryan. It's not what I want. I want dv dt. I'm given I and I want dv dt. I'm in trouble. What do? Start chanting. I equals c dv dt. Look at this. I equals c dv dt. So what happens? dv dt is 1 over c times I of t. I got it. I got it. That means dv dt evaluated at t equals 0 plus is 1 over c times I at t equals 0 plus. So I have to take a derivative. I got to take a derivative. So I say, okay, I got to take the derivative of this equation up here. So I need to take the derivative of that. And my colleagues, if you do, you get this. I then set t equals 0 plus. So that becomes here 1 over c times I at t equals 0 plus. This equals 1 over c times 0.5 because the current was 0.5. That was given. And this then is K1 e to the s. T is 0. Then this term goes to 0 plus K2 e to the 0. Solving, we get K2 is that expression there, and we're done. How are we holding up? We have 50 minutes. We'll get it. All right. You okay with this? Okay. Tiger, what do you think so far?
It really takes a long time.
Really takes a long time. Okay. Tara, it just seems to be unanimous. It's taking a long time. Okay. Now, tell you what, I just want to show you one thing from the other exam, if I may. Okay. So, my colleagues, I'm now going to open Spring 2017 version 2. How do I know it's version 2? I got the M in the name. Now, my colleagues, this is essentially the same problem. I strongly encourage you to do this problem also. This is the other second order problem. The only other way I know how to ask it, Parker, is we just solved for the voltage. Now I'm going to ask you to solve for the current. So tell you what, let me just do part A. Parts B and C, was there a D? I don't think so. Parts B and C are similar to the other problem. Here, let me just do part A for you. Okay, let me just do part A. Okay. All right. I ask you for the current. All right. Here we go. The final push. I ask you for the current. Second order system. What do you always do? Take a walk. Okay. So take a walk. Now we did this morning. We did this morning. I know you're going to get it. Take a walk. Minus Vs plus R times I of t plus L di dt plus the voltage across the capacitor equals 0. Now, I don't want the voltage across the capacitor. I want the current I. I want to get rid of that V sub C of t. I want to know, I want to be able to write it in terms of I. How do I do that? I equals C dV dt. So what I can write this as 1 over C I of t dt equals dV sub C of t. I now integrate this from 0 plus to t, from 0 plus to t, and my colleagues, I get this right here. We did this morning in our class. V sub C of t is all of this. What do I now do? I take V sub C of t and I plug that into here. Okay? So what I get L di dt plus R times I of t plus V sub C of t. V sub C of t is 1 over C, the integral from 0 plus to t of I of t dt plus V sub c at t equals 0 plus. Okay? All of this equals Vs. That should be what we have here. Now, my colleagues, from this morning's lecture, what do? I take the derivative of that. I get this. And Emily, once I get this, I put it into standard form by getting a 1 in front of the second derivative. And we get this here. What do you think? Jerry?
Is it just me, or does it look exactly like the equation from the other problem, except it's I of t, except instead of v of t?
I think it is. Isn't that interesting, Jerry? Jerry is saying, doesn't this look almost identical to the other one, except the variable is changed? I think what's different also is the right-hand side. In one case, it was Vs over Lc. The other case here, it's 0. And that makes sense too, Jerry, because the capacitor opens, so the current is going to be 0 in steady state. Jerry, did I do okay? How do we do? Now, the rest of the problem I'll leave to you. Now, there's one last problem. Tell you what, this has been a lengthy review so far. We've gone for an hour and 20 minutes. Why don't I just get you started on the last problem? And my solutions are all there. Okay? So why don't I just give you a little push, and then we'll call it quits. Does that sound okay? All right. So I'm back to version 1 of spring 2017, exam 2. Determine an expression for V out as t approaches infinity. Tara, I thought this was simple. Our colleagues told me it wasn't. I thought it was. Jerry, I thought this wasn't too bad. Here's what happens. Close the switch. Let t go to infinity. Constant input. What happens to the capacitors after 5 tau? They become open. So you see, look what I get. Open, R1. Open, R2. Open. R1 and R2 are in parallel. What's the voltage? IS times REQ. That was it. Did we do okay? Thank you. I didn't think it was hard. But some people didn't see it. See, if you didn't see that the capacitors became open, you tried solving it, and you went into like a deep space, and you may never come back. Okay on this? Now, there's a part B and a part C. Let me do part B, and then we'll call it quits. Determine the complete solution for V out. You don't have to determine an expression for the time constant, but determine an expression for K in your solution. So, my colleagues, here's the deal. This is a first order system. No, it can't be. I saw 2 capacitors. These capacitors can be combined, though. Or 3 capacitors. They can be combined. So this is a first order system. Now, what do I know about a first order system? V out is ke to the minus t over tau plus the right-hand side. But Ryan, what's the right-hand side? Particular solution. The value as t goes to infinity. That was part A. Part A of the problem. And we say, oh, that's R1, R2. How could that be difficult, I heard someone say. Over R1 plus R2 times IS. So now, V out is ke to the minus t over tau plus this. I say, fantastic, I got this. Now, we are given, Parker, that V out at t equals 0 plus is 0. I gave you that. So you let that equal 0 equals ke to the minus t over tau. That's ke to the 0. Plus this. Solve for k. And as they say in England, done and dusted. You then substituted that in. Now, that was the short way. Now, Tiger, some people prefer to do it the long way. So if you actually wanted to write the nodal equation, you could do it. You get the same answer. But I think this was pretty easy. By knowing that the solution is ke to the minus t over tau, Ryan, plus the value as t goes to infinity. The value of the voltage as V out as t goes to infinity. Are we good? Now, the last part of the problem. My cursor. I keep losing my cursor. The last part of the problem determine an expression for the time it will take V out to reach 70% of its final value. How are we doing?
I don't know how you expect us to do this all.
You can do it. Okay. Determine an expression will take for V out to reach for 70% of its final value. What's the final value? This. What's the solution? V out equals this plus this. This was the value of k. Now, my colleagues, the time to reach 70% of the final value is V out has to be 0.7 times the right-hand side, the particular solution. So we then say 0.7 of this equals this plus this. What's the one thing I don't know, Michael? T. Solve for t. And we solve for t taking the natural log. And we actually are going to do this entire test. And we get t is tau minus tau times natural log of 0.3. You didn't have to solve for tau. How did I do? Look over this last part again. This is kind of interesting. You never know when you might see it again. We've done 3 problems plus the other way on the second order. So we've done a lot of work in about an hour and a half. How was it? Was it worth your while? All right, my colleagues, we've had a long first day together back from spring break. Jonathan, Matthew, Jesse, Sean, thank you. I'll say goodnight. Signing off from Pierce 116. Thanks, everybody.